Thank you very much. Thank you, everybody. So this is the first part of a 3-hour lectures on the structure of the proton. So here I give a list of references that go in much greater depth than what I can do in 3 hours. So I will upload the slides so you can have a look at those. So the original goal of my lectures was to give an overview of our understanding of the structure of the proton from Feynman parton model to modern QCD picture, and then to introduce the basic concept and technique behind the PDF global fits. And I want to show you that, understanding the PDF of the proton, so that parameterize the inner structure of the proton is not a boring task at all, because there are lots of ingredients that are involved in it. So there is non-perturbative effect, perturbative QCD, all the experimental measurements, lots of things about statistics that I have to keep learning about, and higher order predictions, and machine learning, and everything you want. So it's a really big world in which you learn a lot about many things. And then I want to discuss PDF-related phenomenology at the LHC mostly, and also some EIC and beyond. But I was lucky because Professor Sturman gave a great introduction about the parton model, so I can skip that part and kind of guide you more into a trip inside the sausage factory. So really how PDFs are made, the dirty secrets about PDF sitters and things like that. So I guess that many of you are like this guy, like the average physicist who wants to do any phenomenology at the LHC. So you're there in front of a shelf, which is the LHA PDF library, and you have to pick a PDF set and decide, which one you want to use to give a number to the experimentalist, right? How many of you use the LHA PDF library? Yeah, Doreen, quite a lot of you. Okay, so many of you are PDF users, all right? And I would like that by the end of these 3 hours, you have more criteria to answer these questions. What do PDF uncertainties mean? What kind of effects they really include, how reliable they are. That's a very subjective thing, but I would like to give you the instruments to answer this question. And how do we interpret the different predictions that we get by using different PDF sets? And how do we shall we pick all a set out of the PDF supermarket and take an envelope? So there are lots of questions really that when we talk about precision physics, we want to answer to. So I would like to give you some of the criteria. So I think the first part will be more of an introductory thing, and then I have a lot of things I could discuss this afternoon, but I would like to hear your input about what things you're most interested in at lunchtime, so I can select which slide to show in the afternoon. Okay, very good. So let me just give, I'm sure the other lecturers already mentioned that we are at an exciting time because really the LHC has entered the precision era. So we had an extremely successful run 1 and great performance at run 2. And clearly as luminosity increases, we have not only a stronger probe of known processes, but also larger mass reach into unknown processes that we can reach either directly or indirectly. And really, the LHC is at the forefront of the exploration of the high energy regime and a key to plan future colliders. And we really need to have precise prediction in order not to miss the opportunity, okay? So how do we compare an experimental event? Okay, that's not really the experimental event, it's already a simulation of an experimental event. So this is what, for example, the CMS detector sees. So this is a proton-proton going into a top, which then decays into a bottom, the W, which in turn decays into a muon and the neutrino, a Z, and the jet. So how do we describe, from the theoretical point of view, this event, and we compare to what is observed in terms of the experiments? So there is this nice picture that many people use is by this Sherpa artist. So, the idea is that it's a mess. So it's probably it's less nice than the experimental picture we had before, but it shows the idea that really the division of scale that we have allows us to make sense of this mess and try to describe it, because we split this complex process into different parts, and we try to make the best prediction we can for each of these parts, and then we put it all together and we provide a theoretical prediction. So we have the hard scattering of partons, or the partonic cross-section, which we compute in perturbative QCD and electroweak theory. We've got the parton distribution, which are these pink bubbles that describe the proton in terms of partons. And then we've got all the parton showering and hadronization effect. And then we've got even more complicated thing like multiple parton interaction, underlying event, and so on, okay? But the idea is really, in a sense, divide et impera, like the Romans did. So we have the collinear factorization. So for two protons going into any final state AB, that's the kind of collinear factorization that you often see in this kind of lecture, no? Which is valid in some regime. It's these infrared safe quantities that, that George was talking about earlier. And there would be lots to say about each of these terms, but in these lectures, I really want to focus just on these two functions, which is what we call PDFs, which are the universal function within the collinear factorization theorem, because that's important. So when we talk about universality, is because we are in the collinear factorization framework. Beyond that, the universality is not proven. Even here it's proven only in some processes, but okay. That parameterize the proton structure. Okay, this is just to set the scene. And so why we care about PDFs and PDFs uncertainty? So I think there were different motivations in the past. So for example, this is one of the first fit when the PDF dependence, so the different parton probability function dependence was extracted from the data. So these were really like the lines, I don't remember. So there is the valence quark distribution here, D valence plus U valence, then there was the gluon here, and there was a dotted line, the quark valence. Okay, so this was 1984, was really like a great thing, the fact that you had this function that could really kind of prove the collinear factorization, the universality of this function, that you could really draw, you could really extract from Drellian data, deep inelastic scattering data, neutrino data that were available at the time, functions that were a property of the proton, okay? So this was really a kind of test of collinear factorization, okay? So having these lines was already a huge success of all the framework of QCD and collinear factorization. But clearly now, you have usually all these pictures, so where we don't just want to have one single line, we want to compare the different extractions of these functions, the different groups extract from the data, and we want to compare their uncertainty. So you always take one of these lines as a reference, and you plot all the other lines, and you try to understand how do we make sense of these uncertainties, and how, why sometimes the PDFs do not agree within uncertainty if you determine them in a different way. If they are universal functions, so why are they different if you use different methodologies, okay? So why is this PDF? So for example, in this case, so these are all the gluons that 5 different groups determine. So it would be the equivalent modern version of this line, okay? And so why do we care to know whether this is the real uncertainty or the real uncertainty should be the envelope of all of these lines, okay? I will tell you like some examples of why we care about this uncertainty and why we want to reduce it. So for example, Higgs physics, no? So one of the big goals of the LHC is to characterize the Higgs and to understand whether it's a standard model Higgs or if it's a portal to some new interaction that we haven't measured yet. So if there is a broader sector, and to do that, we really want to have a precise theoretical prediction within the standard model for the Higgs production. And these are the 5 main production channels ordered by cross-section. This was the Higgs Yellow Report, 2013. And you can see that the total theoretical uncertainty, which is given as a percentage of the cross-section here, is split in 2 components. So the red component is the one due to missing higher orders in our perturbative expansions. Okay, this is usually evaluated by varying factorization and normalization scales. That's something I don't have time to talk, but this is something that as we go up with orders, so as we compute the next cube leading order in the perturbative expansion of the cross-section, as we add resummations when they're needed, this is an uncertainty that usually goes down, okay? But then there is another component, which is the blue one, which is the PDF uncertainty. So how the uncertainty we saw in the previous line translate into an uncertainty on the cross-section due to our lack of knowledge of the proton structure, okay? So this is the blue component, and clearly you can see that for many of these processes, in particular vector boson fusion or TTH, whatever, so there is a limiting factor in the precision that we can achieve in theoretical prediction due to the PDF uncertainty, okay? And here we go to the yellow report 2016, and we see that we went up with the order, so we also had the VBF at next cube leading order, so the scale diminishes, also the PDF uncertainty goes down, but still you can see that there is this kind of dominant effect of PDF uncertainties, okay? So if we want to do precision physics, we want to reduce the uncertainty of these functions, okay? Then, also determination of the standard model parameters. So this is not the most recent. There was a recent one that came up, 1 month ago, but still, I think the message is the same. If you want to extract the W mass from the LHC data, one of the dominant sources of uncertainty is really the PDF uncertainty, okay? So if you see at all the systematics, in the previous determination, the PDF uncertainty was dominating over everything else, okay? So in this case, for example, the QCD uncertainty was much less than the PDF uncertainty in the modeling of the distribution, okay? Then clearly, if you believe that we can produce some new physics particles, like two gluinos, and typically they are heavy because we have excluded most of the light particles, at that point to produce some heavy particles, you really need to get partons that carry most of the fraction of the proton. So you really need to know the large X parton distribution function. So what's the probability that a parton carries a large fraction of the proton momentum? And these are really unknown. So at large X, we have a very little knowledge of the proton, okay? So if you, in a sense, if you see a bump, you see a bump. But if you want to characterize it in terms of new particles, then you need to reduce this uncertainty. And the other thing, which is what I'm mostly interested at this moment in my research, is somehow history teaches us something. So at some point in 1995, when there were some JETS data at CDF, so there was a big discrepancy between the QCD calculations here and the data, okay? So it was as if there was a bump at large jet transverse energy. And there were a lot of papers about contact interaction, some kind of new physics explanation of this difference that was observed. But at the time, there was basically no information on the PDF uncertainty, so all these lines didn't have an uncertainty related. And also there was basically no knowledge of the gluon at X larger than 0.1, okay? So a gluon that carries more than 10% of the fraction of the proton. Then the CTEC collaboration, which is one of the oldest collaborations that started to do the fits of this function, included this data into their fit, and suddenly the discrepancy went away, okay? So that's very important because it tells us two things. On the one hand, that whenever we claim a discrepancy, we need to be certain of what are the uncertainty. But the other thing is that, it's a tricky thing because that's something that we can do even now. So we can always try to put more and more data into our fit because we are greedy. We want to decrease the uncertainty of parton distribution function, and we might absorb some new physics effects. But I will tell you more later. Okay, very good. So parton model, this part I just have a very sketchy calculation that I want to show you on the board, and that's it, because the QCD lectures gave a much deeper overview. I just repeat what was already said, that in 1967 was the first deep inelastic scattering experiment at SLAC. It was 20 GeV linear collider, and gave the first evidence of something that was very surprising at the time, like points like elementary constituents, which were later identified as quarks. So here is the kinematics of DIS. And the surprising result at SLAC was that the structure functions that describe the proton structure did not vanish as you increase the scale of the collision. Rather, they remain finite and constant, and they only depending on xb. Okay, so this is the Bjorken scaling, and this was what was measured to an incredible precision by the SLAC data. Okay, and this scaling, as it was already pointed out, pointed to the fact that the exchange vector boson, like the photon in that case, was dominating at that scale, was scattering elastically of some point-like objects that had no mass or scale associated. Otherwise, you would have a dependence on the scale. So it's as if the lepton scatters of charge spin 1/2 constituents, and this is because of the relation between F1 and F2, that carry a fraction x of the proton momentum. Okay, this was Feynman-Parton model, and that was described already. But then it's interesting because, okay, that's not an historical overview, but as we started with the Hera collide that had a much larger center of mass energy, we already go to a center of mass of 318 GeV as compared to 20 GeV. So these are the energy of the electron beam and the proton beams. You can see that the scaling that was observed at SLAC, so this is the F2 structure function, is still true if we are at large Bjorken X, okay? So large but as we go to small Bjorken X, you do see clearly a scaling, so that the structure function do depend on Q squared, okay? And this is beautiful because this is exactly predicted by perturbative QCD. So when you correct the Parton model and you start including QCD correction, you do actually go from this formula, that was the one that was shown yesterday, where you can see that the cross-section for the scattering of an electron off an hadron was just the incoherent sum of the partonic cross-section times these probability densities, to something which is what we call QCD improved Parton model, in which both the partonic cross-section and the PDF depend on the scale μf. So how does it happen? I want to show a very heuristic calculation, but it shouldn't take more than 2 blackboard, in which you show that in QCD, the collinear singularities, so remember we talked about soft and collinear singularities in the previous lecture, that arise when partons interact via QCD interaction are absorbed into a redefinition of the Parton distribution functions, which, as a result, acquire a dependence on the scale. So let me try to do this calculation. So I tried to simplify a 20 pages note, which I will share with you, into like 4 maximum blackboards. So it will be sketchy, but I always like to do this calculation because it makes me understand in a very kind of heuristic way what happens when we talk about these things. So, okay, this is what we saw yesterday. We have an electron of momentum L, which is scattered off a proton. Okay, so that's your proton. This is one of the partons, which we know. Let's look at the quark case. So here we have a quark of momentum p hat, which is what is called xi p, okay? And then here we have the scattered parton, which has momentum xi p plus q, where q is the virtuality of the exchange boson, okay? This is what we call x. So what we do now, so this corresponds to the formula over there, okay? So the partonic, I don't write it anymore. So now we want to add QCD corrections, okay? So let's do it explicitly. So in particular, I want to just look at this bit. So I want to put everything that happens here, okay, into a bubble. Okay, so just imagine that you have an incoming quark, and here is what is in this bubble here. It's a process, okay? It doesn't matter. It could be anything. Indeed, we will see that in the limit which I consider, it doesn't matter what happens inside this bubble, okay? So we just have an incoming quark of momentum p hat that does something here, okay? So to that, I want to add real and virtual corrections, okay? So let's do it explicitly. So if you do a real correction, you emit a gluon of momentum k, and as a result, the momentum that enters this process is p hat minus k, okay? But we also have the virtual corrections. P hat, here you have a loop where you have a momentum k, p hat minus k, and you have p here, okay? So to do this calculation explicitly in a very sketchy way, let me just define the momentum k of the real emission in the Sudakov parameterization, okay? So k, I write it like in the basis of the p hat, kt, and mu. So let me tell you what I mean. 1 minus z p hat plus kt plus alpha eta. So this is the Sudakov parameterization that you might have seen in other calculation, where the basis is given by p hat, kt, and eta that are chosen such that you have p hat dot kt. So these are all four vectors equal to 0, like eta dot kt. Eta squared is equal to 0. And also is equal to 0, and 2p dot eta is equal to 1, okay? So if you can choose in particular, let's give an example, which is the one where I'm going to show these things. You can take P, like some energy, which I call P naught hat, 1, 0, 0. So I take the incoming parton into the z-axis direction. Then eta will be, because of this condition, 1 over 4 p naught 1, 0, 0, minus 1. So this is the opposite longitudinal direction, in direction of minus z. And then kt, it's the other two, x and y, is the transverse momentum plane direction. So you've got kt, let me call it two component, kt1, kt2, 0, okay? The important thing here is that when you impose the conditions over there, you have some limit. So let me just. So you can prove, it's in the notes, that imposing the condition up there, you know that z has to be smaller than 1, and also kt is smaller than I've given kt max, which is the function of the energy of the incoming parton. And the other thing is that the alpha that you have in that parameterization is something of order modulus of kt square 1 minus z, okay? So that's important, because whenever we will do explicitly the calculation of the real emission, this part, the part that involves alpha, is also of order kt square. So it will not give the collinear divergence, okay? Very good. So all of this can do it analytically. So what happens? Now we want to do the real emission. So in particular, we want to compute the first order QCD correction. So if we want to do the first order QCD correction to this process, so we need two things. We need the phase space and we need the matrix elements, okay? So phase space, you have just, the extra phase space you've got here is the K particle, the emitted gluon. And you can write D3K If you do a change of variables and you integrate over the azimuthal angle, you can write that like d kt squared, so the modulus square of the kt, divided by 16 pi squared, because I integrated over the azimuthal angle, so one of the pi goes away, and then you've got dz 1 minus z, okay? So keep that into account. So, and then you have the matrix element. So if we just calculate the matrix element square, again, you can do it explicitly, it's in my notes, I just write the result. So you have 2, the strong coupling constant square, GS, divided by KT square. So this comes from this propagator here, because P square is 0, K square is 0, so you just have 2P dot K, which we know is equal to KT, okay? And then you have the color factor CF, and then you have 1 plus Z squared over Z. And then you have the, I just write, so M0 is the amplitude for this process, okay, which is the one that you had before, where instead of having an incoming momentum P, you have an incoming momentum ZP, okay? Because if you think in terms of the longitudinal momentum, the emitted gluon takes away 1 minus Z, so the quark that is left as a fraction Z of the original momentum of the parton, okay? Very good. You put it together, putting also the phase space, and the interesting thing is that you find the first order correction due to the real emission, EQ, of P hat. So GS squared over 4 pi is alpha S, so we do alpha S divided by 2 pi, color factor CF, and then you have something. So this Z comes from the phase space, 1 minus Z, again comes from the phase space, 1 plus Z squared, and then you have the integral over KT that goes up to the maximum kinematics you can get. And then you have sigma hat EQ 0, so the cross-section you would have for the tree-level. Plus, so this is just the divergent part, okay? In the notes you have all the finite terms, but here I want to focus on the divergent part, the most divergent part, okay? Here I basically leave out in the finite all the terms that don't have the KT, that cancel the KT2 square divergence over there, okay? So these are all in what I call finite. But so what kind of divergences do you see in this expression that I wrote over here? When does this thing diverge? 2 divergences. Yeah? So which one? Exactly. So you've got 2 divergences. So when Z is equal to 1, this diverges logarithmically. So you have to send 1. So I'm going to do some really kind of regulator. So of course it's not good from the gauge dependent, but just to understand the physics, I think it's good to do some cutoff in the integration. So let's send 1 into 1 minus epsilon, and the other divergence is here, is the collinear divergence. When KT goes to 0, which really means when the parton is emitted collinearly to the original parton, you have another divergence over here. So you have to send this 0 into some kind of regulator, which I call lambda squared, okay? Which eventually then we want to send to 0, okay? Good. But the good news is that, again, this is all very sketchy, but when you add the virtual correction here, this thing gives you something. So now we are doing the real, now we are adding the virtual correction, and again, it's done in my notes. You see that this gives you minus sigma hat of EQ of P hat alpha S over 2 pi CF, and here you have 0, 1 minus epsilon dz over 1 minus z, 1 plus z squared, and here you have the same thing, dkt squared over kt squared. Okay, so the good news is when you put the two of them together, this term, you see that when z goes to 1, you have sigma of zp hat minus sigma of p. So the numerator, when you added up these two terms, cancel the soft divergence, which is what we know because virtual and, if you have infrared safe quantity, virtual and real correction cancel each other, okay? Very good, but we are left with one singularity. So let's look at the singularity because this is where PDFs enter. So now if we put everything together, you still have this singularity alpha S. So now I can extend the z integration up to 1. It's not a problem, sorry. The z. But I have to keep this lambda squared, okay? And here I have 1 plus z squared, 1 minus z, sigma hat 0. Okay. So what do I do again in this? So I'm gonna split. So this clearly, the kt part is just a logarithm, okay? So what you can do is just you split this integration between lambda squared, which is what I want to send to 0, and kt max squared into 2 bits. So you put all the singularity into the first bit. So now I'm going to split this integral between lambda squared and mu f squared, which is my factorization scale, and mu squared to kt squared max, okay? So what did I do? Nothing, like simply splitting the logarithm in 2. But now, what happens is that when you put together the function, so you see that there is something that I just did. So I put this part into the finite bit. So now whenever I write sigma 1 EQ, so this is the original, so the 3-level cross-section, okay, plus alpha S over 2 pi. Let me write this thing as dz p q q z. And then I have sigma hat 0 EQ z p hat. And now I have this log of mu f squared over lambda squared, plus all the finite terms, okay? So I'm left with this singularity. What is PQQ? It's this function here. Why do I call it PQQ? Because it doesn't depend. I didn't know anything of the bubble, of what was happening in the process that the parton is participating to. This just depends on the emission of a gluon in the collinear limit, in which I only keep the singular terms in kt squared, okay? So, but I still have this logarithm that bothers me, all right? So let me just tell you another thing. If you do the same thing, again, it's done in my notes, but clearly, if you are in QCD, you can have an incoming quark inside your process, not only for the gluon that emits a quark that emits a gluon, but also from a gluon that splits into a quark and anti-quark, okay? So if you do the same game and you keep only the singular part, you also have this process, which is important. You have a gluon that emits a quark and an anti-quark, and again you have a quark that carries the fraction z of the original parton that goes in there. And if you do the same game, clearly you don't have a leading order term for this, okay, because you don't have the sigma 0, but you have this sigma hat 1 of Eg. So imagine we only have two partons, the quark and the gluon, okay? Yes?
So similarity is still there in P, right? That is where you are going to involve in the parton distribution. It is still there, right?
What is still there?
One is there, one is like log mu square upon lambda square, one is there. I am talking about peak. So even after subtracting out,
it is still there.
So when you subtract it out, it was supposed to be soft divergence will get cancelled out.
Exactly.
Like the real and virtual will cancel out, but collinear is still there.
Exactly.
So this log should not be there, right? Because otherwise you still have again, even after subtracting out
this log, I haven't finished. That's not the final product. In fact, it is a problem that it's still there. You need to do something, okay? And to do something, you have to put all this expression with this log that is righteously bothering you into the kind of total cross-section, okay? Because this log is what will go into a redefinition of the PDFs. Okay, so now I'm just doing this thing, showing you that the log that is bothering you is there also in this other channel, into the gluon that splits into a quark and anti-quark. Again, if you do this calculation, you do have, you don't have the tree level, but you have alpha s over 2 pi dz between 0 and 1 of pqg. So it's another universal function that is different because you have the gluon splitting into that. So you have, and then you have, again, but it's proportional to sigma hat of EQ ZP, okay? And the same log which we want to get rid of, plus finite terms, okay? So now we have calculated the QCD corrections to that, okay? In a very rough way. Now we want to put it back into our parton model formula, okay? So remember what we had in the parton model formula. I hope to finish in this thing. So we had that equation there. Now we have calculated E sigma hat EQ to the next order, okay? And we want to put it back together. So what do we do? So we have that sigma of EH PQ is equal to, so we have the integral between 0 and, imagine the sum is only between Q and G, okay? So let's simplify. You have 6 quarks, 6 anti-quarks, but okay, let's just do 1 quark and 1 gluon because this is what I want to point out. On d psi here, and then I have sigma. Instead of that sigma, I put sigma hat that I computed, which gives me sigma naught EQ of xi pq plus alpha s over cf, the integral dz pq q z sigma hat naught EQ of xi zp, right? And the log of mu f squared divided by lambda squared. And this multiplies phi q, the probability of finding the quark q into the hadron H, carrying a fraction xi of its momentum. And then I have plus, remember we also had the gluon contribution alpha s over 2 pi of the same thing, okay? So let me PQG Z sigma hat 0, that's the same thing, xi ZP, and the same log. And here I have phi G H xi. Okay, so when I put this thing back, what is the trick? Now, what's plus, remember, we have all the finite terms that we have discarded. Okay, so what is the dirty trick that I'm doing now? I redefine this function. So now phi of q, which is the kind of bare Parton distribution function that I had in the Parton model, becomes phi of q, of q h of xi mu f. So it does acquire a dependence on the scale. And is equal to, again, here I had to do some trick, but anyway, the integral between xi and 1 dy over y phi of qh, so the original one, times, I have a delta function of 1 minus xi over y plus alpha s over 2 pi p q q of xi over y and the log plus phi of g h y alpha s over 2 pi p q g xi over y log of mu f squared over lambda squared. So if you do this redefinition, so basically you put this divergent logarithm into a quantity that now depends on the scale. But at that point, again, like renormalization, we don't care about that scale anymore. So it's everything defined into a kind of experimentally measurable quantity, which is the Parton distribution functions, okay? If you do that, at that point, you have two things, so two consequences, and then I finish. So the first one is that now sigma EH of PQ can be just written really like the sum, the integral of now a sigma, which is finite. So what I'm left with is just the finite bits, EQ, but that also depends on mu f. Because remember that the log that I pushed into the finite part now has a dependence on mu f. So I have this times phi of q h xi mu f, okay? Plus, okay, the bit that depends on the gluon, okay? But it's, so the magic that I did by reabsorbing this collinear log into a redefinition of the PDF is that now I have a factorized and finite cross-section. So sigma hat is now finite, okay? I have reabsorbed all the collinear divergency into this phi, into the Parton distribution function. And the other thing, which is what is going to call the D-Glap evolution equation, is that you see that now you have that the cross-section depends on, sorry, here I should put also mu f. The cross-section depends on an unphysical scale, mu f. So again, if I ask that the physical cross-section doesn't depend on an arbitrary scale, which is the factorization scale, which I introduced to get rid of the collinear divergency, you have, as a result, a kind of RG equation of these functions here. So you say that mu f delta phi q, what did I call it? H of psi mu f. This is equal to alpha s, at least in this simple picture, psi 1 dy y p q q psi over y phi q of psi mu f plus p q g psi y of phi g h. Okay? So, of this really kind of sketchy picture, it teaches us, first of all, that to define a collinear and infrared-safe partonic cross-section, we had to do something to the PDF. And this allows us to write the cross-section in terms of finite thing that we can compute up to higher twist power correction terms. And it also tells us how these functions evolve as a function of the scale based on QCD perturbation theory, okay? So because these functions here, which is called the splitting functions, are calculable in perturbative QCD. And the third thing, which is the reason why even if you waste a bit more chalk, I want to always put the gluon contribution, it tells us that the evolution of the quark with the scale is always coupled of the evolution of the gluon with the scale. So the quark do not evolve independently. And this makes sense because quark emit gluon and gluon emit quarks. Okay, so there is always a connection. There is always a talk to between quark and gluons, which is given by the D-Glap evolution equations. Okay, so later on I will send you the actual notes where you have the full calculation. But I think that even here. It's something that when I did it the first time, I understood better the kind of improved Barton model, so I wanted to share it with you. Okay, very good. So let's go back to our work. Do you have any questions on that? Okay, good. So here I just pretend that there was only one quark and one gluon inside the proton, but when you do the full thing, when you put all the flavors in, what you get instead of this equation, you do actually get a 13 couple integral differential equations, which are called the D-Glap equation, because these people who discovered them, and actually the original papers are really beautiful to read. So these 13 couple differential equations, which are the ones that I wrote here, so here, this is a 12 times 12, because at least at leading order, you got the same for quark and anti-quark, the splitting functions, okay? So you have, this is a 12 times 12 thing, and then this is the quark gluon and QG. So you have to do some kind of thing. Then you can always reduce these 13 times 13 integral differential equations to 11 decoupled. So you do quark combinations that are decoupled from the gluon. Okay, you can basically diagonalize this matrix maximally. And if you diagonalize maximally, you have just two terms that are coupled to each other, which are the singlet and the gluon, where the singlet is the sum of all quark and anti-quark for all flavors. Okay, so this is the combination that you cannot decouple from the gluon. And then you have the other kind of combinations, which are the valence quarks, so U minus U bar, D minus D bar, which instead decouple from the gluon, okay? So this is just a matter of diagonalization of the matrix. And the splitting functions are known up to, I should say, next cube leading order. So we know them fully up to next leading order. This is an incredibly difficult calculation, actually, because you've got off-shell partons. But now there are most of the bits that we need to go to n-cube leading order, which are coming out and this is very important because we are at a level of precision where some of the partonic cross-section have been computed at next cube leading order, and if you really want next cube leading order PDFs, you need to know the splitting functions to next cube leading order, okay? And this is a massive calculation that some people are doing, okay? Mm-hmm. Sorry? Yeah, No, that's that. In principle, yes. If you take a scheme in which all the quarks are massless, you have also the top. If not, you have 2 times NF, number of active flavor, plus 1, which is the gluon. Yeah, 13 is a kind of, I should have said 2 NF plus 1. Thank you. Yes?
So is this differential equation is kind of incomplete? Because here what we are considering, since it is an energy dependent differential equation, like, so here are only first order terms coming. Like you can generate a quark by your anti-quark at second order, right? So anti-quark will be there, a gluon emitted, and then gluon again went into quark and anti-quark. So in that sense, it will contribute that in second order. I mean that QG multiplied by Q bar, something like that.
Yes, it's true. You do have, the structure is more complicated if you go to next leading order because of what you said. So the PQQ is not, you have the PQ and then you have to add an extra term because of the splitting into Q bar. Which different, in fact, usually what you do, you give the splitting function in terms of the singlet, the gluon, and all the different kind of linear combination that do not depend on the gluon. And these are the same at leading order, but when you go to next to leading and next to next, they start to differentiate to keep into account exactly the fact that you are mentioning.
So this is formally up to first order. If we are considering for first order, then we can, this is true. And if we are going for NNLO, then I think we should consider quadratic product term like product term.
No, yeah, you don't have quadratic terms. It's just a different combination of this matrix. You just reshuffle the terms inside this matrix, but in a different way. But the structure is still a block 2 times 2, and then all the non-diagonal. It's not that the matrix becomes more complicated that you need quadratic terms. It's still the same.
Or maybe these PQQ already considering the like. So it can contribute to 0 order also, first order also, second order also. So it already is contributing. So
yeah, exactly. So these are expansion in alpha S, and you never see them in this form. You always see in the 2 times 2 and the non-diagonal and diagonal terms. And in that thing is cleaner. It's true that when you see it like that, you think, but what if then quark becomes an anti-quark and you start mixing things up? Then you don't write things like that. But in a sense, it's the same thing schematically. You diagonalize, and then you can do the things that looks right at all orders. But yeah. Thank you. Okay, very good. And the interesting thing, so, okay, this is an integral differential equation. So to solve it, you need the initial condition, okay? So if you know, so this is what I was mentioning. This is the coupled differential equation of the gluon and the sum of all quarks and anti-quarks. So you can solve it. Of course, it becomes more complicated as you go to higher orders, okay, because you have expansion in alpha S, but in a sense, there are all the public evolution code of PDFs that you can download and use and see how they're done. And that's what I wrote in my PhD. But what you need, so basically what it's telling us is that if you want to know what is the gluon as a function of x at the scale mu squared, you want to know what is the singlet combination of quark and anti-quark at a given initial scale, mu naught squared, and the gluon at the initial scale, mu naught squared, okay? So you need the initial condition, and once you know the initial conditions, then you can evolve with perturbative kernels, okay? So these perturbative kernels, you can see them as an exponent of combination of the splitting function alpha s and b naught. Okay, so I didn't want to make it heavy by writing explicitly, but anyway, what I mean to say is that because then you can expand the exponents. So basically, the structure of the splitting function tells us how the quark and the singlet evolve with the scale. In particular, this is the gluon as you increase the scale. So what happens? You see that basically at large x, it stays more or less there. So it's slightly depleted, okay? And at small x, it explodes, right? So as you go to smaller and smaller x and larger scale, the proton is mostly made by gluons, okay? And how do we see it? So this is interesting because this comes from the splitting function of a gluon, of a quark splitting into a gluon. No, yes, QG is the diagram in which you have a gluon splitting into quark and anti-quark. And this has a singularity in 1 over x. And also the PGG, the gluon splitting into two gluons, has a singularity in 1 over x. So this is what gives you this exploding behavior at small x, okay? Already looking at the leading order splitting functions, it tells us how you expect the PDF to evolve as you increase the scale, okay? And remember, the scale is the kind of hard scale we associate to a process, because when you do write the factorized formula, you have the PDF computed at mu f times the partonic cross-section, q squared over mu f squared, and you want to make that ratio small, okay? So this is really the scale of the process. Okay, and the same for the singlet. So the singlet, which is this combination which is coupled to the gluon, it has the same behavior. Yeah, this is because of the coupling with the gluon, okay, anyway, but it has the same behavior that it goes up at, so basically the high X gluon fits the growth of small X gluon and quarks. And this, sorry.
However, before you show us this splitting function that depends over x, 1 over x, and so you say when we go to OX, somehow the gluon explodes.
Yeah.
I don't have 1 over x as the denominator, but still I say increase the OX.
It explodes much less, if you see, in a sense, because it's a second order effect. It's driven by the sum rules. So here, I don't know, maybe I should remove this example because it's not something that you see from the splitting function behavior. You see it more from the sum rules, and it's not written there. Yes, no, you're right. Instead, what you see here for the non-singlet, so for example, the combination, so this is the U valence, which is U minus U bar. You see here that because the combination of splitting function that describes these diagonal terms doesn't have any divergence at small x, at that point, sorry, you just see that, at small q squared, this is centered about 2/3, okay, so the x, so because you've got two valence, U quark, up quark, and one down inside the proton, so it's centered about 2/3, and then as you go to higher q squared, the parton lose the longitudinal momentum onto the gluons, so the distribution shifts to lower values of x, okay? So in a sense, the gluon can always be seen as a kind of indirect effect onto the quark evolution, even when they are not coupled to the gluon, because, the sum of all the parton momentum has to be 1. So if it goes away into the gluon and the singlet, then the valence will have less momentum, okay? It's a kind of rough explanation, but that's the meaning of it. Any questions? Yeah?
I have three basic questions regarding this singlet and non-singlet one.
Mm-hmm.
So what does it mean to one to be singlet, giving singlet contribution or non-singlet contribution? What does this term, singlet or non-singlet?
So singlet is the combination that is coupled to the gluon in the evolution. So it's the sum of all quark and anti-quark, in a sense. In the kind of heuristic derivation that I said before, So no matter if this is a quark or an anti-quark, the same thing happen, okay? So you don't have differences in here. So, so this is what I mean by the singlet. So it's the combination of quark and anti-quark that behaves in the same way when you have this emission. If you instead take the non-singlet are the ones that are decoupled from the gluon. It's really like yeah, again, it's you have to go. I will do it later. In a sense, you have to go to the diagram and see explicitly which ones, in considering the quark and the anti-quark, you cancel the contribution of the gluon. Okay, you see explicitly at the diagrammatic level. So if you, for example, okay, I don't want to say something stupid, but I think that if you take a quark minus then an anti-quark, so you always take combination where you have quark minus some anti-quark, and this cancels the divergence that you have from the gluon. I don't remember, but I think Lance can help me on that.
Well, one way to cancel it is what you said. So U minus U bar, it doesn't mix with the gluon. D minus D bar doesn't mix with the gluon. But also U plus U bar minus D bar.
Exactly.
Doesn't mix with the gluon. I think that's what people usually mean by blood singlet.
Yeah, it's
basically, you can take any sum.
Any sum where.
That up to 0.
Exactly.
Think of it as proton minus neutron. The gluons think the proton and neutron are the same.
Yeah, exactly.
And so they cancel in that their contributions to the evolution. Let's say a proton minus neutron.
Exactly.
The gluon does not carry any isospin. So when we construct U minus D, you're constructing a pure isobector, whereas U plus D is an isoscalar. And that's why it can mix with the gluon if you add D bar plus D bar.
Exactly. Thank you. Very good. Okay, so what do we need now is the initial condition, okay? So because once we know what is a PDF at some initial scale, okay, at some scale at which they are parameterized, then using perturbative QCD and solving the gap evolution equation, we can evolve them to higher scale, okay? So everything we need to give a prediction at the LHC is to find the PDFs at some scale. Okay, so typically what we do, we parameterize the PDF at some initial scale, we extract them from the data, and then once we know them at a given scale, we know them at all scales. Okay, this is the magic of the gap evolution, up to the precision that is clearly the precision of the splitting kernels that you have. Okay, that's it. I think that's something I've already shown. And the other magic thing that, again, was very heuristic there, but is what was mentioned before, is the collinear factorization, is that these PDFs, for inclusive enough processes, that's very important, these PDFs are the long distance part of the cross-section, and they are independent of what happens at the short distance, okay? This is the principle of universality of PDFs, okay? So whether you have a DIS process where you have just one PDF at a time, or a proton-proton collision when you've got two PDFs, we assume that these PDFs are always the same. This is the reason why people can do global analysis of PDF, by extracting them from experimental data that involve both one proton or two at the same time. Okay, so no matter what happens, whether you produce a lepton pair or you produce a Higgs, whenever we do give prediction in the collinear factorization framework, we always assume that the PDFs are the same. Okay, so, sorry, go ahead.
Just a question, but then, okay, when we think, for instance, calculation of parton shower or NLO match to parton shower, we still use the PDF, even if this is not inclusive, because we produce events that are fully exclusive, and then we feed whichever distribution we want. So, in principle.
This is because the unitarity, when you are inclusive, you sum all over the phase space, and that effect is equal, gives you 1. You know, it's only, so that's the reason why whenever you do this kind of fits, you only want to have inclusive cross-section, because if you're looking at some specific corner, you know, saccati-dependent observables, at that point, you have to go beyond this framework, okay? And at that point, so the key word is inclusive enough observables. So we never put in our fit observables that need parton shower. For example,
I am worried about the opposite.
Hmm?
I am worried not for what you are doing,
No, no.
the fit, but about what we are doing when we do an LO plus PS and we use standard PDF there.
Yeah, that's interesting because I will mention, so for example, at some point we did compute PDFs that were extracted by including next to leading log soft gluon resummation. And indeed, we saw that if you put these in the theoretical prediction you use in the fit, the PDF changed than if you use like a standard fixed order prediction. So sometimes the effects of the resummation into the partonic cross-section is enhanced because this is not kept into account in the PDFs. But it's a small effect, but it's true that, I don't know, people do talk about this problem sometimes, so it's not irrelevant at all. Okay. Very good. So that's, I just repeating what I said. So thanks to the PDF universality and the perturbative evolution, we can extract the non-perturbative X dependence from a wide set of data that involve initial state protons, okay? Clearly in the future, people might be able to extract them from lattice. At that point, we should do something else. In a sense, at that point, probably this is not needed anymore, but it still would add information. But at the moment, all the information we have on PDFs do rely on these global fits of observables, okay? So let me tell you what are the ingredients in a global fit. So first of all, you have to choose a set of experimental data that you want to add into your fit of the function, and you want to include them into your fit with all information, the correlation between the different data and inside each of the data sets. You choose some theory settings, so the theoretical prediction that enter the cross-section here, so what we call sigma hat, are all theoretical predictions that are done at a given perturbative order with a given heavy quark mass scheme by including or not including electroweak correction, whether you include intrinsic charm or you don't include intrinsic charm, given value of alpha s, given value of, so there are lots of things that go into your sigma hat. These are all computation done with some given theory settings. Then you choose a starting scale, Q naught, which is not too low, where perturbative QCD still applies because you are evolving from the scale up to the scale of the data. And you don't want to go too down because otherwise then the DGLAP evolution doesn't work. And then you solve the DGLAP equation from the initial scale to the scales of the experimental data, and you build the observables. And then you fit the PDFs to the data. And then you also want to provide error sets to compute the PDF uncertainty. So you want to extract a function and an uncertainty in this function due to the finite knowledge we have from the data. We will talk about it more after lunch. And in the end, then you give basically all these member sets to the LHA PDF user, and they can compute the PDF uncertainty for any phenomenological study, okay? So there is a lot that goes on. So I split the kind of thing into 3 bits, so it's a complex machinery. So now, before lunch, I will go through a bit of the experimental data that we include and which combinations are constrained by the different experimental data. After lunch, I will talk a bit more about the statistical framework and the theoretical calculations that go into it, okay? Very good. So experimental input remembers that we are not measuring the PDFs. They are not measurable function. So we only measure what is on the left-hand side, which are observables that convolute the PDFs with partonic cross-sections, okay? So this is important. So it's not a trivial fit. it's, so we always fit a function that goes through some integral and some sum over the integrals, okay? And the other thing which is important is that we always want to fit observable for which this formula is accurate enough. So observable that don't have large correction from the power suppressed terms, okay? So this means that we cannot take all the data that we have. Typically, we want to exclude the low Q-square data and the very large X data, because there is where we have higher twist terms or power suppressed terms. So typically we always go Q squared larger than 2GV squared. Actually, we should go a bit higher at the level of precision that we have. And we always put the cuts on W squared, which is this variable, so the partonic center of mass energy, and that cuts away the very large X region where there are elastic effects that we do not understand and higher twist effects that are enhanced, okay? Very good. Okay, and so why we need to put a lot of data? Because different data constrain different PDF combinations. So the sum that you see here in DIS and in the hadronic processes is important. So now I want to guide you through the different data that we have. So typically, this is, you put the kinematic coverage of the data. So this is a plot that you might have seen in some of the PDF talks. So here you see basically the leading order kinematic, which is the kind of Bjorken X in the case of DIS, or then I show you explicitly what it is in the case of hadronic processes, okay? So this is the X that is constrained into the leading order kinematics by a given process, okay? And here you see the scale of the experiment. So for example, if you measure the Z, you are somewhere here, because Q squared is 91 squared. If you measure the W, you are here. But you can see that all these measurements are performed at different rapidities, and this changes the X of the PDF that is probed by these data. So I hope that this thing, so we'll go through this thing bit by bit, and I hope it will become more clear in the next 15 minutes before going for lunch. And the different colors correspond to the different type of observables that are typically included in a fit. So let me go through one by one. So the big green portion that you see here are the HERA data. So this is really deep inelastic scattering for the electron-proton collider. And you can see that why there is this line here, this is exactly the variable y that you saw yesterday that is related with Q squared over XS. S is the center of mass energy, so you have this dependence. It cannot be larger than 1, and this gives you this diagonal cut over there. And the HERA data cover a broad region of X, because the Bjorken X that is measured there goes between 4 × 10⁻⁵ up to 0.6, okay? Remember, the Bjorken X is what magically corresponds to the X of the partons in the parton model, but the Bjorken X is an experimental quantity, depends on the angles and the energy. So it's a macroscopic quantity that corresponds to the fraction of momentum carried by the partons, okay? And the Q square, again, goes between 3GeV squared up to 5 × 10⁴. I think it's, yes, Q squared, okay, yeah.
These are, I mean, all data HERA or only those that you plug in the PDF and the rest is cut?
Yeah, these are the ones, so the cut is dictated by the process. It is not a cut that we put. It is the definition of the inelasticity that is less than 1. You know, it's not a cut that is nature puts. Yeah, exactly. Then these are the deep inelastic scattering data that we include. I didn't put here, for example, the jets. So the jets that are measured into electron-proton collision. I only put the structure function measurements and the combinations, okay? So these are the events. It's something that you saw yesterday as well. So this is the jets that comes out of it. So you've got an electron. This is the incident electron. That's a scattered electron. And from the kinematic, you reconstruct what is the Q, what is Y, what the Bjerk and X of the event. So in this case, it's a really exactly. So the electron is scattered back and has an energy of 300 GeV. So basically, really measuring the energy in the calorimeter, you basically get all the parton kinematics, and you can see that, for example, this event constrains a region of X which goes from 0.47 up, okay, because you integrate between XB to 1, okay, so this is what I mean by constraint. Then you also have charge current event where you have a W that mediates the deep inelastic scattering, so you don't see the outgoing lepton because it's a neutrino, so you just see the incoming electron or positron, and you see missing energy, which is the one corresponding to the neutrino, but you can reconstruct it from the jets. So these are data that are a bit less precise because of the missing energy. So the more precise are the neutral current one, the one that are mediated by a Z or a photon. These are less precise, but are very important. And the other thing that I wanted to show is, you can see here, so these are measurements of the cross-section. This is the reduced, sorry, I should have shown first the, okay, here, that's important. So what they measure in most, it's a combination of F2 longitudinal structure function, which is something that starts on next to leading order, so you don't have it at leading order because it's F2 minus 2x F1, so it's 0 in the parton model. So this is the longitudinal components that you only have because you have QCD. So this is the kind of reduced cross-section that are measured by HERA. So it's interesting that because of the F3 function, which is the one that depends on the parity, you get a sign plus or minus in front of F3, depending on whether you have an electron or a positron. So just to, before, then I go back to this, but it's interesting because you can see here that you have very precise measurement of these quantities, and you can see the split between the electron initiated, which is the red curve, and the positron initiated function, which is exactly the measure of the contribution of F3. Okay, so this bit, which is the one that contains the axial part of the current. Okay, so it's something that you can see at larger X and at larger Q when you go about the mass of the Z, because if you don't have the Z, you don't have any F3 contributions. Okay, so you really need exactly the epsilon term that you saw yesterday. Okay, and very good. So what is interesting is that why do they measure that? Because depending on Y, so these Y plus Y minus are just combination of elasticity. So I think I forgot to write it, but it's just 1 plus or minus 1 minus Y squared. So these are the contribution of Y plus Y minus, okay? And Y is the inelasticity of the event, okay, is what you defined yesterday. And you see that playing with these three kinematic factors, you do measure different combination of PDFs, okay? So for example, for when you have a neutral current scattering, you always have combination of Q plus Q bar with different couplings, depending on whether you're looking at the gamma or the interference of photon and Z or just the Z. And for F3, you always have the combination of Q minus Q bar. Again, in my notes, I have an exercise that shows why you get the minus sign when you do this combination. For the charge current is interesting because you have different combination of U plus D bar, plus S bar plus C, and F3 minus U minus D bar. So basically, you just kind of play with linear combinations so that in each value of X, all of these functions are constrained, okay? So this is the best you can do. And the longitudinal structure function, which starts at order alpha S, it's also interesting because it depends on the gluon. So that's something that shows indirectly the presence of the gluon, because somehow it's a pure QCD So if you didn't have gluon inside the proton, you wouldn't have the FL contribution. So it does measure the gluon where? At small x, because it's where the gluon evolution kicks in. So if you do this kind of measurements at small x, you indirectly constrain the gluon at small x inside the proton, okay? Very good. We still use in this other corner the kind of old fixed target DIS data, so like Chorus, NMC, SLAC, so the very kind of old data, because the reason why we like them, it's, okay, they have a large uncertainty, but they do give a strong constraint on the PDF. You can see it's a much larger X region and lower Q square, lower energy. But because here they are often, experimentally they measure the deuteron structure function, which is a combination of the proton and the neutron. And whenever we look at this data into our fit, we always assume the SU2 isospin symmetry, that the neutron is just like a proton when you exchange U and D, okay? And this is good because these experiments, they often measure quantities like the ratio of the deuteron structure function over the proton structure function, and this gives a handle of the U over D combination at large X, which is not constrained by Hera, okay? So these data are precious because we play with that. And indeed, it shows also complementarity between the collider and the fixed target experiments. So for example, at JLab, they're doing really precise measurements of, modern measurements of these quantities. And you can see, because it's interesting, because they really not only constrain the valence due over U ratio at high X, but also because they test nuclear model in the X to 1 limit, where the isospin symmetry is not, so it's much more complicated. You should really correct the data by this kind of effects. So I think it's really interesting because they really can constrain large values of U over D up to 0.85, which is very important also for new physics. Okay, then quickly, I think is what George mentioned yesterday. So depending on what you observe, sometimes the fixed target DIS data like Chorus also measure some exclusive cross-sections. In particular, they tag a D meson in the final state, and that's particularly important because if you have a D meson in the final state, which comes from the fragmentation of a charm quark, because of the CKM enhancement, here you always have a dominating strange contribution, a strange that goes into a charm, which is bigger than a down quark going into a charm. So these are kind of measurements that we are kind of attached to because it's one of the few handles that we have on the strange quark, which otherwise, given that it's a C quark, is kind of washed away by the up and down distribution. So measurements like this that were measured by Chorus and NUTEV are still important in the fit to measure the strangeness of the proton. I'm gonna go faster. So other things that we have are the Drellian data. Here you can see that we have all the on-shell measurement of the W and the Z at the LHC and at Tevatron. And here we have some high mass and low mass Drellian when we look at the outgoing leptons into the high invariant mass or low invariant mass region. And we also have some fixed target Drellian data from all the Tevatron experiments. So what PDFs they constrain, you just write the leading order process. You see we have the luminosity of QQ bar. For the case of neutral current Drellian, is the same flavor, or you've got Q U D bar or DU bar for the W. And again, the reason why we like looking at the old experiment is because they have proton-deuteron scattering and proton-proton scattering. And again, this gives us access to something that if you had PP, you wouldn't really see it because you always have that the quark dominate over the anti-quark. So this gives us access to the D bar over U bar ratio I will show maybe after lunch why this is important also for new physics searches. So these are, again, data that are old, that rely on some probably old nuclear model, but we are still attached to them because they give us information on some combination that otherwise we wouldn't access. Okay, that's it. And yes, and how, yeah, that's it. I think I don't want to be too fast, but if you're interested for some process, you can come back to me. But how do I look at, so what are the X that are constrained, for example, by a measurement of the production of the Drellian, okay? This is simple, you have the Parton formula, so this is the mass of the produced particle, square root of the center of mass energy, and then you have e to the plus or minus the rapidity, okay? So if you want to constrain larger value of x, you go to larger invariant mass. So if you look at the Drellian distribution at large value of the lepton invariant mass, you are constraining larger value of x. If in the central rapidity, if you play like LHCb with larger value of rapidity, for each event, you are constraining one parton at very large x and one parton at very low x. You understand? Because if y is large, x1 gives you a large fraction and x2 gives you a low fraction. Okay, so this is why we say that ATLAS, CMS, and LHCb, they have a complementary kinematic coverage. So this is shown here. So LHCb covers this rapidity region between y equal to 2 and y equal to 4.5, which means that it covers this region of x between smaller than 10 to the minus 5 and smaller than 10 to the minus 4, and this larger region, okay? You can see this as a function of the invariant mass they discover. While ATLAS and CMS, they cover more the central region, so the kind of intermediate X range, okay? So this is how to find your way on, okay, if I measure that, what kind of X in the parton am I constraining? That's it. W plus charm is important, and we still don't have an NLO computation because, again, W plus charm complements, so thanks to the CKM enhancement, constrain the strangeness inside the proton. So this is complementary to the chorus measurements, and actually there is a bit of a tension between those. And then, let me go very quickly, I just have 1 minute. So the gluon, I said before that the structure function, so the Bjerken scaling violation is dominated by the gluon at small x. So if we only had DIS data, we would know indirectly the gluon at small x. How do we constrain it at large x? Because we need it as well. How do we do it? This is too much. We have 3 processes that are measured really precisely at the LHC, which are the inclusive jet cross-section, TT bar production, and ZPT. And they all have, as dominant parton channel at the LHC, a gluon-initiated channel. Okay, so this means that if we measure these processes and we put them in our fit, we have a strong handle on the gluon. I will show you later that there are some tension between these data. And again, how do you know what are the X constrained, for example, by a jet measurement at PT equal to something and pseudo rapidity equal to something, you use this formula, okay? So the larger is the PT probed by the jet, the larger is the X of the partons that is probed by that particular measurement, okay? So this is how you reconstruct the kinematics of the jets, and you can see that the jets really go at large values of X and very large energies. Okay, that's it. I don't want to bother you for too. Okay, that's the top. It's a similar thing. I think I am done. There are other processes like direct photon production, but I can talk to you offline if you're interested. Anyway, so to summarize, we have a very large covering from the LHC. So I showed more or less where all the regions are and how all these different measurements, when we put them in the fit, constrain different regions of X for the gluon and for the quarks. And I want to say that it's great looking forward because, for example, the EIC which will start soon, is going to give us a very complementary constraint with some modern technology into the low energy and high X region. And we have a lot of different LHECs. So everybody does this kind of plot that I hope now you understand better to see how even new experimental data can help us constraining the structure of the proton at different values of X. And that's it. Okay, thank you very much. Questions? Yeah, I will show it later. I have a table where I show which data is included by which PDF group. The answer is no. So there are three kind of global fitting PDF collaboration, like CT, MSHT, and NMPDF. And more or less, the HERA data are the same, but there are lots of choices you can make on the LHC data in particular. And that's something that determines the difference in the shape that I showed you at the very beginning. Yes? Yes?
What is the origin of twister
The origin?
terms? Of twister terms. Twister terms.
Higher twist. Higher twist.
Yeah.
Higher twist. Origin of higher twist.
Huh. I'll let George answer. I don't know. No, in a sense, it's really like all the, so when you go, sorry, we have to go. Higher twist terms. So the higher twist terms are really power corrections that you get beyond the collinear factorization. To be honest, I try to put it here, but it's a very intuitive picture. Where is it? Yeah, so basically these are the contributions that connect the spectator with the outgoing part. So that's something that goes beyond the kind of collinear factorization that I was showing here. When you start connecting the lines or things that you factorize in the normal collinear factorization, you start adding these terms to the operator product expansion. So you have the leading twist and the next to leading twist. So that's something is done in the Pesking book. It's done, so you can look at the IS in the operator product expansion, the next term in the expansion that you ignore when you do the collinear factorization is the next to leading twist. But to be honest, I never, I always kind of ignore them. So, again, I think we're getting to the point where we should start thinking about those. Because somehow I always happily ignored until now there are more and more processes that they say, you should really start considering these terms, even when you put a cut on a PT and so on.
Yeah, like if they are contributing approximately in the same order of N3 errors, then there is no point in doing like more and more higher order correction and not considering the twist term.
Yeah. The thing that is good now is that at the moment the low Q-square data have a large experimental energy, so these effects is not comparable. So in a sense, it's an effect that is within the experimental uncertainty, but of course, if you go to the EIC, at that point you cannot do that. So if you want to do serious fits, you have to add these effects. The problem is that I don't think they're computed in, so you need to put some modeling into these effects. So you have to be careful to estimate what is the uncertainty related to a particular model that you use